Hello and welcome. So in this tutorial we are going to learn about implicit surfaces, which is a new feature added in Houdini 22, which allows us to create mathematical geometry representations which can have infinite resolution, which means that we can sample them at any position, and it does not need to have any kind of volume representation like STF or standard volume representation, which does have a limited quality too. And we can also do multiple operations on multiple implicit surfaces. So let's see them by dropping down a geometry network, and then over here if you type isurf, you will get all of the implicit surface tools. So we'll start with this implicit surface node, which creates a basic implicit surface geometry. Right now it is representing a box shape, and you can create many other basic geometry shapes. So for example, sphere or torus or tube or a plane, and they all are represented mathematically. So we can sample them at any position, and we will get the SDF values accurately, that if we are outside the surface or inside or on the surface. And it might be better than SDF, but you might remember that we also have mathematical primitives for basic shapes in Houdini. For example, if we take sphere or a box, you will see that over here on the primitive type parameter. So if we set it on polygon mesh, you will see that we have polygon faces, 288 of them. But if we switch it on primitive, we only have one single primitive, which is sphere type of primitive. So this is also mathematically represented primitive, and if we go to a box and turn this to a primitive instead of polygons, we will also see that it also gets fit into this single primitive, which is this hexahedron primitive, and this is also mathematically represented. Then what is the difference between these and the implicit surface geometry representation? So if we immediately click to see the geometry info of this implicit surface, you will see that it is represented using another primitive too, a single primitive, but it is a packed geometry. And obviously at the center of that packed geometry we have a single point. And if you drop down a unpacked node over here and connect this, you will see that at the end it is also a sphere primitive. So what is the difference between this sphere primitive and this implicit surface? First of all, when you create this implicit surface node, the geometry which is shown in the viewport is only for visualization, so it is not the actual implicit surface. That's why we are seeing this primitives being used here. And what actually represents the implicit surface is this point, which contains many point attributes. For example, this implicit surface string attribute, and this shape string attribute, and also the transform attribute, which is used to represent the rotation of this implicit surface. So what is the difference between this implicit surface and the old primitives of these basic surfaces? So for example, what if we want to do an operation between these two primitives? For example, if we want to boolean them, so if we want to cut a box out of this sphere, if we make it a little bit bigger, we would like to see something like where this sphere gets cutted by this box. But if we boolean it, you will see that it doesn't work, because the boolean node is only meant to be worked on the polygon or face primitive types. But that is not the case for this surface. So if we alt click and drag this implicit surface node to create a copy and set it on box and increase this sphere's size a little bit, 1.3, to, for example, cut this box out of this sphere, we can use the implicit surface operation node, which can take two surface nodes and do any kind of operation on them. For example, or let's cut out the sphere from the box. That will look better. So let's reset the uniform scale, make it a little bit, we have to make it lower a little bit. So now we will like to see this sphere cut this cube like this, as we are seeing in this visualization. So we'll set the display flag on the implicit surface operation node, and you will see that if we set the operation on subtract b from a, you will see that nothing happens over here, because as I said before, these geometries are just for visualization. But since they are represented mathematically, we can use the implicit surface slice node, which is just like the volume slice node, but it works for implicit surfaces, and it will show us the actual implicit surface. So if we set the display flag on this, and we can change the scale of this sphere a little bit so that we get to see the box. And as you can see, the sphere is cutting through the box, and that we can see through this implicit surface slice node, because it samples those the mathematical function created by these implicit surfaces, and then we sample it at a certain resolution, and we get this kind of visualization. So you will over here see the voxel size parameter, which is the resolution of the voxel grid used to sample this implicit surface. And we also have the implicit surface convert node, which can use, for example, a volume grid to sample the implicit surfaces mathematical function using a VDB, and do that for all of the voxels, and then we will have this sign distance field representation of it, as you can see. And you can lower the voxel size, for example 0.02, and then you will get more and more resolution, and it is not limited at all. And you can also sample the implicit surface at any position using vex. So for example, if we drop down the attribute Wankel node and set it to run over detail, and then we can use the implicit surface function, which is new to Houdini 22, to sample this implicit surface at any location. So if we connect the geometry to the first input, now we can use the first input as our implicit surface geometry, and you will see that it also wants a vector pos, and you can also give it many reference parameters to get many kinds of other attributes. But right now we are only interested at the TF sample value, so we'll give it a position, a dynamic position using parameters, so CHV, and we'll name it pos, and then we'll store it in a float attribute. So if we see the help for this, you will see that it returns a float value. So we can store that into a F8 val, and then if we set the display flag and go to the geometry spreadsheet and detail, you will see that if we create a sphere parameter, and then we can drag this parameter on the viewport to create a pivot handle for this. Now it is inside the this. So if we turn on this show handle, you will see this pivot handle, which is representing this pos. So we can move it, and you will see the sample value changing. So for example, if we take it inside the box surface, you will see it getting close to 0, which is where the surface of this implicit surface is. And if we take it inside the sphere, which is subtracted from this box, you will see that the value starts increasing, and we get more and more farther from the actual surface. So these are the three ways you can actually see the actual representation of this implicit surface. So let's see that how it is actually working. So if we set the display flag on this implicit surface node after the operation and go to the geometry spreadsheet, so over here you will see the actual flow of implicit surface operations which are being made to make our final implicit surface in this implicit surface operation node. And now these implicit surface and all the other implicit surface related attributes will finally make sense. So as we saw before on these single implicit surfaces, you will see that we just have a single kind of shape. On this node, it is a rounded box, and we union that, which means we add that to our implicit surface, which creates this basic single object. But when we do an implicit surface operation between multiple surfaces, you will see a chain of procedural implicit surface operations being built over here. So over here, first I will tell you in normal words. So first over here, as you can see, it unions this rounded box into the implicit surface. Then it moves it to another memory, you can say buffer, and then after that it adds this implicit surface to node, which creates a sphere. You will see it over here. So it adds it in another group, and then we just subtract this sphere group which we create over here after this group begin, and we subtract it from the cached box we had cached before this creating this group. So if we read it in the geometry spreadsheet, it will happen top to bottom in the order of the point index. So first the implicit surface operation of point 0 will happen, and then 1, and then 2, and then 3, and just like that. So over here, as you can see, we are starting a group. I think it is not very necessary, this one, because we don't have anything before it. So but it starts a group, and what this group begin implicit surface operation does, as I said, it catches anything above it, and then it starts another group, which is the other implicit surface operation below it. So for example, we have this union one, it gets added to this group, and then after that we start another group begin. So it catches all of the above ones. So it catches this round box into the memory, and then we start from an empty implicit surface, and then we union the sphere, and then over here you will see a subtract implicit surface operation with a group in shape. It is not an actual shape which we can see, but it means that this implicit operation now gets the last created group's items, and then it subtracts it from anything that was before it. So we had a rounded box, and then we started the group for the sphere, and then we ended the group, and then the shapes which were in that group came inside this surface operation, and then we merge it with the whatever that was in the previous implicit surface operations using this subtract implicit surface operation mode. And then we just have this another union operation for the previous group, which won't do much, but it is just here as a placeholder, and this will give us this and over here you won't see the actual boolean, but it is now creating a implicit surface which has a sphere subtracted from a box, and you will be able to see that surface by using this, for example, this vert node, and this is the result. And as you can see, this system is totally procedural, just like other Houdini things. So it happens procedurally one by one, and any step of the implicit surface creation can be changed. And we can also specify over here on the implicit surface operation node that how we would want any kind of subtraction or union or anything which works on multiple implicit surface. How would we want the blending between those shapes to happen. So if we go to scene view again and see the implicit surface convert, let's set the voxel size to 0.02 so that we can see better. And now you can make the blending between these two shapes, for example, smooth, so it would look much smoother, or you can make it round, or you can chamfer it, which means that it will cut in sharp angles, which will give you more sharp blending between these two shapes. And just like this, we can keep chaining this implicit surface operation node, and it will keep making chains of these implicit surface operations to procedurally depict our implicit surface. So we can just click and drag this and use it with another implicit surface, which can, for example, be a sphere. We can translate this so over here, and now you can see this in the implicit surface convert, and this is how it works. As you can see, the evaluation of this is very fast, so it is really good for things like collision geometries for solvers. This is why side effects has added the first solver which can be which can use implicit surfaces as collision shapes directly, and that is the COP level Pyro solver. So I will show you that. So let's delete this, and also this implicit surface convert. You can drop down in null, and this will be our out collision. So now we can create a COP network, and we can make use of the ready-made Copernicus Pyro recipes. So we can drop down a Pyro fireball, Pyro configure fireball. It will be good. And we have to focus on the collision points of this, which is a geometry input, and it takes this Pyro collision shape node. And this is the node which is the collision shapes for this Pyro solver block, and we can also provide it our custom implicit surface. So we can drop down a SOP import node over here, and we'll import our custom collision, which we have made using implicit surface. And you will also see that it is actually importing giving us right now. This collision shape node is a basic implicit surface. So if you middle click on this, you will see all of these implicit surface attributes we have already talked about. So we can provide our own implicit surface, and now this will be our collision shape. And I will also lower the voxel size of this whole simulation so that it runs faster. Also because I am running on OpenCL on the CPU, which is very slow compared to running it on GPU. And we can actually see the actual VDVs for this, so we don't need to use this image as our reference right now because I have currently lowered my voxel size a lot. And now we can increase the source shape size so that so now let's see, and we can also change the uniform scale of collision shape so that it is a little bit larger. Let's set it on 1.8, and then we can change the voxel size to something higher now, to 5. Now let's run. As you can see, the collision shape is perfectly working as we expect, as you can see, and it will get the effect will be more obvious when you decrease the voxel size, but I can't do that because I am running it on my CPU and it is very slow. And in the Copernicus context, you can also use the new implicit surface header, which is provided in the OpenCL, to also evaluate the implicit surface over there so that you can make custom solvers and other kind of COP nodes inside COP network using OpenCL, as well as in the geometry level using the OpenCL geometry node. I have already showed you that how you can use it in Vex, but there is also a big example on how you can use it in OpenCL Inside that header above it, you can see, and if you have seen my previous video, you might know that how you can see those headers. So you will have to take a look at the implicit surface header, and that has a big example at the top, that how you can use it in your OpenCL node. And also they have in the recent daily build, they have provided the implicit surface headers for HDK. So in future production builds or in the daily build, in the latest daily build, you will find them and you will be able to create C++, for example, SOP nodes or DOP solvers using implicit surface geometries. And it is a really nice way to make collision surfaces, and it is much better than SDFs or the old parametric primitives which we couldn't do much things with. So I hope you liked this video. After this video, I will probably make an video on Apex. So I will see you in that video. So thanks for watching.